Of regular polygons. If you look around this page, you'll notice all sorts of regular polygons that occur naturally, or somewhat naturally, in the real world. If you look at the soccer ball, I was a big avid soccer player. You'll notice that there's a lot of, I guess those are hexagons on this soccer ball that kind of cover the soccer ball. I think there's another shape that's on there as well, maybe pentagons, depending on your soccer ball. So there's all these different shapes that are regular polygons. There's another, these are paver stones. These are basically used to make little pathways whether you're on a cobblestone street or whether you're in your backyard making stones. This is a spider web, and as you go towards the center, this very center shape that's here, though it's not necessary, depending on the size of the spider web, it's going to be some sort of regular polygon. Obviously a stop sign, which is man-made along with the soccer ball, is going to be an octagon. 8 sides. And also in beehives, you'll see a similar pattern to what you have with a soccer ball with the hexagons. I'm not sure where you might be at school, but this is a molecular compound. And generally speaking, the strength is found with the different bonds, and those might be signified by the different colors. But there's also a shadow in here, which kind of makes it hard to see. But generally speaking, there's like a lot of triangles, and sometimes those triangles are regular triangles depending on the bond. So we're going to talk about regular polygons today in an effort to try to figure out the area of them. And this is kind of extending the idea that area of quadrilaterals or area of triangles. We'll kind of take and combine those two concepts today into this area of regular polygons. So whenever you have a regular polygon, remember that means that it's both equilateral and equiangular. Okay, this doesn't work with just regular octagons or regular hexagons or anything else, but only for regular polygons. What you can do is you can divide a regular polygon into congruent isosceles triangles. Okay, so basically you draw segments from the center of the polygon to each vertex. So from here you draw to each of the vertices, just like so. The center of the polygon is actually called the center of a circle that surrounds the polygon. So these kind of are like radii. So these congruent segments are sometimes called the radii of the regular polygon. So each one of these is the same length. That only happens because, again, it's a regular polygon. This is a pentagon, and you're going to have, let's see, 1, 2, 3, 4, 5 triangles for this pentagon. Remember, a pentagon also has 5 sides. I wonder if that's a coincidence. Let's try it out with this hexagon. The hexagon, you have n equals 6. When we draw these to each of the vertices, looks to me like we're going to have, let's see, 1, 2, 3, 4, 5, and 6 different triangles in here. And hopefully, if I was to draw this really nicely, they'd look like this, where all these are going to be isosceles triangles. What's kind of neat about these is this side length, the side length of each of these is going to be the same. Why is it the same? Because this is an equilateral pentagon. So each of the side lengths are the same. So each of these triangles we could prove are actually the same by side, side, side. Let's try this out with this, I guess this is called a septagon or a heptagon. 1, 2, 3, 4, 5, 6, 7. It has 7 sides and 1, 2, 3, 4, 5, 6, 7 triangles. So I'd be willing to make a bet that this octagon here is going to have 8 sides, that this 13gon is going to have 13 sides and 13 triangles, and this 15gon is going to have 15 triangles on the inside. Let's see how that might relate with what we're talking about. What's the area of one isosceles triangle in terms of S and A? Well, let's look at our picture. S turns out to be the side length, so of this triangle from here to here. For the triangle, it looks like the base. And A looks to me like the height of the triangle. So if we remember, the area formula for a triangle is going to be 1/2 our base times our height. Well, for us, that's going to be 1/2 our base is looks like it's going to be S, and our height of our triangle is going to be A. So using these things, we're going to say that our formula here for area is going to be 1/2 S times A. And how many congruent triangles in a pentagon? Well, a pentagon again has 5 sides, so we're going to say 5. So what is the area of the entire pentagon? I'm going to say the area of the entire pentagon is going to be 1/2 S times A, that's the area of the triangle. And how many triangles were formed? Well, there were 5. So 1/2 S times A times the number of triangles. Okay, next we have a regular hexagon. Remember the hexagon has 6 sides. What's the area of one isosceles triangle? Again, that's going to be 1/2 S times A. That's what we found on the last page. How many congruent triangles are there going to be? Well, there's 6. So I would say the area of the entire hexagon is then going to be, well, this is one triangle. And then we're going to multiply that by 6 because there's 6 triangles. So again, the area is 1/2 S times A times your number of sides, or your number for this, for the polygon. Regular heptagon. Remember, heptagon has 7 sides and it looks like 7 triangles. The area of one isosceles triangle, one more time, 1/2 S times A. There's 7 congruent triangles. So the area of this is going to be 1/2 S times A. That's the area of the triangle times the number of triangles, which is 7. 1/2 S times A times your number of triangles. Okay, the distance A, it appears in the area formula for a regular triangle and has a special name. It's called the apothem. The apothem. Maybe practice saying that, apothem. It's kind of a neat word, one of my favorite words in the English language, apothem. When a regular polygon is divided into isosceles triangles, the apothem is the height of each isosceles triangle. And that's what we talked about. This apothem turns out to be the height of these triangles. So let's make this conjecture. The area of a regular polygon is given by the formula A equals 1/2 S times A. Remember, that's the side length, that's the apothem, that's the area of the triangle, this whole thing, times the number of sides. A is the area, capital A, lowercase a is the apothem, S is the length of each side, and N is your number of sides, or that turns out to be your number of triangles as well. Okay, so 1/2 S times A times N. I've also seen some people write this as S times A times N divided by 2. And some books call the S something different. Sometimes they call it the length of the sides. So you'll see 1/2 lan sometimes, or lan divided by 2. What we're going to stick with is we're going to stick with this formula up top here. Area equals 1/2 S times A times N. Okay. Directions: find the areas and the perimeters. Oh, we didn't talk about perimeters. Find the areas and the perimeters of each of the regular polygons. So to find the area, that's just going to be 1/2 S times A times N. I think it's always a good idea to write out the formula that you're going to work with and then substitute. This shape is a pentagon, so N equals 5. This is my apothem right here. Apothem equals 4. This is my side length, which is 6.2. So I know the area is just going to be 1/2. My S is 6.2. My A, my apothem, is going to be 4. My number of sides, because it's a pentagon, is 5. I'll just multiply these together. I can put them all together in my calculator pretty quickly. And my area equals 62 square units, whatever my units are going to be. Okay, let's take a look at perimeter. Perimeter, if this is 6.2, that means this is 6.2, means this is 6.2. Remember, because this is a regular pentagon, it means that all 5 sides here are going to be 6.2. And we can go through and we could just keep adding this up like so. Or we could kind of simply just say that's the, your side length times your number of sides. So in this case, 6.2 times, well, how many 6.2s are there? There's 5 of them. So we'll say 6.2 times 5, your side length times your number of sides. And that should just give us exactly, let's see, my calculator doesn't seem to be working here, 31 units. Remember that perimeter is always going to be just units, and your area is going to be square units. Let me write that again. That wasn't very nice. Capital P equals 31 units, just like so. Got a little carried away when I was boxing stuff. Okay, this shape is a hexagon. If you don't know it by name, just be able to realize that the number of sides is 6. This is our apothem, the 4. This is our side length. Let's do the perimeter first. Perimeter, again, is going to be S times N. That's our side length, which is 5.3, times our number of sides, which is 6. It means our perimeter equals, that would be 31.8 units. Let's circle this really quickly. We'll move on to area. Area equals 1/2 S times A times N. 1/2 S times A times N. That'll be 1/2. My side length is 5.3. My A is 4, and my N is 6. Quickly punch this into my calculator, and I should be at 47.7 square units. Okay. Now, some people ask me, well, shouldn't your perimeter always be more than your area? And you see over here, this area is 62, and this perimeter is 31. So this area is bigger, and this area is bigger. But you know what? We're not really comparing apples to apples or oranges to oranges or areas to perimeters. That's not what's going on, because these are square units and these are just units. So even though it might appear to be a bigger number at times, it's not necessarily something that you can compare very easily. This is a square, and there's probably a couple different ways we could solve this. I'm going to solve it like it's a regular polygon. So we'll just say the side length is, or the number of sides is 4. So the perimeter is going to equal S times N. Well, what's the side length? It tells us that this piece right here is 6. I kind of need to know the entire side length. So that would be 6 plus 6, which is 12. I'm going to multiply that by 4. So my perimeter simply equals 48 units. Okay. If I'm looking for my area is going to be 1/2 S times A times N. I think it's a good idea always to write out your formulas again. Helps you memorize them pretty easily. Your side length here is 12. Your apothem is 4. And your number of sides is 4. Multiply all these numbers together. 1/2 12 times 4 times 4 should give us 96 square units. And some teachers will allow you to write square units this way, U squared. Some will have you write out the word unit so they know what you're talking about. Just be careful, know what your teacher wants, and you should be fine. There's a triangle, so its number of sides is 3. The side length for this, the S, is going to be 14, and our apothem is going to be 4 if we just identify those. Our perimeter again is S times N. Our side length is 14. Our number of sides is 3. 14 times 3 is 42 units. And our area, 1/2 S times A times N. That'll equal 1/2. Our S is 14, our A is 4, and our N is 3. S times A times N. We multiply this together. Let's put this in our calculators. That should be 84 square units. Okay, so we've seen the shapes. They can give us the shapes. How can they make this different? Well, one way they can do this, instead of showing us this picture, they can actually identify the information and give it to you in words. So let's take a look at one of those. It says you have a regular pentagon. What I have to think in my head, a pentagon means that it has 5 sides. The penta means 5. It tells me my A is 3 centimeters and my S is 4.4 centimeters. Again, find the perimeter in the area. So perimeter just equals S times N. So I'll look up in my problem. Here's my S here is 4.4, 4.4. And I'll multiply that by my N, which is 5. In this case, my perimeter will just equal 22 centimeters. And again, it gave me my units, centimeters, so I don't have to write units. I can actually write what they are. Area equals 1/2 S times A times N. So in this case, area equals, let's see, my S is 4.4. My apothem is going to be 3. And my N is going to be 5. I'll just simply put all these numbers in my calculator really nicely. I should get 33 square centimeters. Woohoo! Here we go. Okay, how could they make this different? Okay, so we've seen them give you pictures. We've seen you just give them words. What if they have you work some of it backwards? So in this case, we're given a regular nonagon. I have to think to myself, okay, N equals 9. It then tells me that my apothem is 9.6 centimeters. Got that. And then it tells me, ooh, my perimeter, capital P, is 55.8 centimeters. So what it sounds to me is find the length of each side. That's the S, and the area. So I have to find A. So S is a question mark. A is a question mark. That's what I need to find. So first off, since they gave me my perimeter, and I need to find a side length, I'll just say perimeter equals S times N. And I'll substitute in the things I know. So that's 55.8 equals my side length, well, that's S, and my N is 9. So I basically have 55.8 equals 9S. In order to get the S by itself, since it's multiplied by 9, the opposite operation is divide by 9. Divide by 9. And S is going to equal, let's see, 55.8 divided by 9. That should give me 6.2. And I know my units have to be centimeters. All right, that's one of my answers. Next, I have to find the area. So area equals 1/2 S times A times N. So that's 1/2. My side length I just found was 6.2. My apothem is 9.6. And my number of sides, because it's a nonagon, is a 9. Okay, I simply multiply all these numbers together in my handy dandy calculator, and I get 267.8 square centimeters. Okay, so what we've looked at today is we've looked at regular polygons. There's lots of them that occur in real life. We've looked at working these problems backwards. We've looked at, just working them as word problems. And we've looked at them when they give you the pictures. Again, I think it's a good idea. Identify the things you know. Your number of sides can be either generated by the name, such as if it says that it's a pentagon, or whether it shows you that it's a pentagon. So identify the pieces that you know, write out your formulas, and just substitute pieces in using your calculators. Be careful to get the right units for each problem, and we should be good from there. Okay. Some of our favorite shapes here, again, we have a stop sign, we have a spider's web, we have the honeycomb, we have some paver stones, soccer ball, and chemical components here. Just a couple things that happen in real life as far as regular polygons go.